Good morning, students. Today we are going to see the topic fiber characteristics. Two important characteristics of optical fibers are mechanical characteristics and transmission characteristics. The mechanical characteristics, the important mechanical characteristics of optical fibers are strength, static fatigue, and the dynamic fatigue. And the transmission characteristics are absorption losses, scattering losses, and the dispersion. Attenuation is reduction in power of the light signal from the transmitter to the receiver, or the end of the fiber link is called attenuation. It is also called as the optical loss. The attenuation of optical fiber is usually expressed in decibel per unit length. Alpha dB LC equal to 10 log pi by p naught. Alpha dP is the signal attenuation per unit length. L is the fiber length. Pi is the input power. P naught is the output power. The basic attenuation mechanism is fibers are absorption, scattering, dispersion, or radioactive losses of optical energy. Next one is the absorption losses. Absorption losses is caused by three different mechanisms. First one is the absorption by atomic defects in the class composition, eccentric absorption by impurity atoms in the class materials, intrinsic absorption by the basic constitution atoms of the fiber material. Atomic defect or imperfection of the atomic structure of the fiber material. Example, missing molecules, high density clusters of atom groups, or Einstein defects in the class structure. Intrinsic absorption means this is associated with the basic fiber material and it's a principal physical factor that defines the transparency window of the material over a specified structural region. Extrinsic or impurity absorption result predominantly from transition metals ion such as the iron, chromium, cobalt, copper and from OH. The transition metal impurities which are present in the starting material used for direct melt fiber ranges between 1 and 10 ppb, causing losses from 1 to 10 decibel per kilometer. Next one is the scattering losses. These losses are more in multimode fibers than in single mode fibers due to their large diameter and large compositional variations. Scattering losses are divided into two types: linear scattering losses, non-linear scattering losses. Linear scattering losses further classified into two types: Rayleigh scattering and the Maillard scattering. Non-linear scattering losses are divided into stimulated Brownian scattering, stimulated Raman scattering. Linear scattering transfers linearly the optical power at one propagating mode to the different mode. Rayleigh scattering, it is the dominant loss mechanism in the ultraviolet region. Its tail extends up into the infrared region. Maillard scattering, it is a linear scattering which arises from the inhomogeneities which are comparable in size to the guided wavelength. Nonlinear scattering losses, when we use high optical power loss, nonlinear scattering losses occur. This scattering causes the optical power gets scattered from one mode to the other at the different frequency, either in forward and backward direction. Stimulated Brownian scattering. This is defined as the modulation of light through thermal molecular vibration within the fiber. An incident photon produces scattered photons as well as a photon of acoustic frequency. This frequency shift varies with the scattering angle. Stimulated Raman scattering. Here, the scattered light consisting of a scattered photons and a high frequency optical photons. Further, this occur both in the forward and backward direction in the optical fiber. The threshold optical power for Raman scattering is about 3 orders of magnitude higher than the Brownian threshold for a given fiber. Next one is the dispersion. Dispersion in the fiber, that means broadening of the signal pulse width due to the dependence of the infrareflective index of the material of the fiber with the wavelength of the carrier. If digitized signal pulses in the form of square pulse are sent, they are converted into the broadened Gaussian pulse due to the depressions. There are two kinds of depression mechanism in the fiber. They are intramodal depression and the intermodal depression. Intramodal dispersion. This dispersion arises due to the dependence of group velocity on wavelength. Chromatic dispersion arises due to the variation of infrared index of the core material with the wavelength or frequency of the light. Waveguide dispersion. This dispersion arises due to the finite frequency bandwidth and the dependence of the mode group velocity with the frequency of light. Intermodal or multimodal dispersion arises due to the variation of group velocity for each mode at a single frequency. Multimode dispersion greater than material dispersion greater than waveguide dispersion. Next one is the splicers. A permanent joint formed between two individual optical fibers in the fiber or factory is known as the fiber splice. Necessary as splicing is, it is used to establish long-haul optical fiber links where the smaller fiber length need to be joined and there is no requirement for repeated connection and disconnections. The types of splicing are fusion splicing or welding, mechanical splicing. Fusion splicing is accomplished by applying the localized heating at the interface between two putted pre-aligned fiber ends, causing them to soften and fuse. Mechanical splice, their fibers are held in alignment by some mechanical means, which may be either by the use of the tubes around the fiber end or V-groove into which putted fibers are placed. This is the animation of the fusion splicing. Next is scribe and break, score and break. A requirement with the fibers intended for splicing is they should have smooth and square end faces. In general, this end preparation is achieved by using a suitable tool which gleaves the fiber. This process is referred to as scribe and break or score and break, as it involves the scoring of the fiber surface under tension with a cutting tool. Next one is the mechanical splice. Can consist of the four type: capillary type, V-groove type, elastic groove type and the spring groove type. The capillary splice type. This common method involves the use of the accurately produced rigid alignment tube into which prepared fibers end as permanently bonded. This tube splice, which is shown in figure, utilize a glass or ceramic capillary with an inner diameter just large enough to accept the optical fiber. Next one is the V-groove splice. This method involves the use of the grooves to secure the fibers to be joined. Here V-grooves is used into which two prepared fibers ends are prepared. Here the joint insertion losses is around 0.1 decibel. Next one is the elastic or elastometric splice. This device comprises the two elastometric internal parts and one of which contains a V-grooves. An outer sleeve holds the two elastic parts in compression to ensure alignment of the fiber in the V-groove, and fibers with a different diameter tend to centered and hence may successfully spliced. Next one is a spring groove splice. This splice utilizes a bracket containing the two cylindrical pins which serve as an alignment guide for the two prepared fiber ends. The cylindrical pin diameter is chosen to allow the fiber to protrude above the cylinders. The complete assembly is secured using a drop of epoxy resin. Thank you.